Start recording. Okay. So last week we started talking about the dot product. Okay. So let's continue with that. We are going to review what projections are, do a couple of examples. So 1 minute. Okay, so let's just review a little bit what the dot product was. So we said that if you have two vectors, let's say V, which is equal to V1, V2, and V3, and U, which is equal to U1, U2, and U3, then the dot product between them, V dotted with U, which is the same as U dotted with V, is going to be equal V1 times U1 plus V2 times U2 plus V3 times U3. So just multiply each component. And we then said that the dot product is related to cosine with the following equation: V dotted with U is equal to the magnitude of V times the magnitude of U times cosine of theta, where theta is the angle between V and U. So if here's your V and here is your U, this angle over here is theta. And it's given, and we have this relationship over here. And another way of writing this relationship is by saying that our angle is equal to cosine inverse of V dotted U over the magnitude of V times the magnitude of U, which is why if V and U are parallel, so if this is your V and this is your U, then the dot product between them, so V dotted with U, is going to be equal to 1. And if they are orthogonal, then the dot product between them is going to be equal to 0. Any questions? Now, the next thing so that's the first thing that we can do with the dot product. And another thing that we mentioned is if your angle is if your angle between V and U is obtuse, or let's start with acute, then because that the angle over here, meaning when they're orthogonal, cosine is pi over 2. Or the angle is pi over 2. So when it's smaller than that, the dot product is going to be positive. And when it's bigger, so when it's looking something maybe like this, now the angle is bigger than pi over 2. So you go from something positive to something 0 when you're at 90 degrees. And then you go and it becomes negative. And then we talked about projections. So if you have two vectors, here's your V and here's your U. And you want to, let's say, first find the length of the projection of U onto V. So that would be something like this. Imagine that you're standing at U and you want to find the shortest distance between this U and this V. And you want to find the length of this distance over here. Well, the length of that distance is going to be, if we use sine and cosine, the magnitude of U times cosine of theta, where this over here is your angle theta. Well, this is the same as saying the magnitude of U times the magnitude of V times cosine of theta divided by the magnitude of V. So we just add a magnitude and we cancel them. And this is the same as the dot product between U and V. So that's this relationship divided by the magnitude of V. So that will be this distance right over here. This distance, this length, is going to be U dotted with V over the magnitude of V. So that's what you do in order to find the distance of the projection of U onto V. Now to find the actual projection, and generally this is called the component of U projected onto V. If you want to find the projection of U projected onto V, this is supposed to be a vector in the direction of V with this length over here. And in the textbook, they denote this U projected onto V. And this is going to be some unit vector in the direction of V multiplied by this number over here, U dotted with V over the magnitude of V. But we know what EV is. EV is V over the magnitude of V. So this is going to be U dotted with V over the magnitude of V squared times V. And that's your projection. Now, my recommendation is to actually not remember that formula, but rather remember the length of the component. So remember that the component of U projected onto V is U dotted with V over the magnitude of V. And then remember that the unit vector in the direction of V is V over the magnitude of V. And then if someone asks you for the projection, just go U dot V over the magnitude of V times EV. And this makes sense. What you're doing is you're going to your projection. So let me make another picture. So here's your V, and here's your U. So you first say, okay, I want to go in the direction of V, so let me find the unit vector V. So that's this vector over here, EV. It's the unit vector in the direction of V. But then I want to multiply that by some length, and that length is this length over here, so that I find this vector right here. And that's the projection of U onto V. And that will be, well, we know what that length is, U dotted with V over the magnitude of V, and then times your unit vector. Any questions about this? Yep. Any questions? Okay. So that's where you first get over here. It's the calculation that we went through. And then over here, you get the formulas. The projection of U onto V. And again, I would recommend to remember this one. U dotted V over the magnitude of V times EV. And this scalar over here, which is the scalar that appears before the unit vector in the direction of V, is called the component of this projection. So they ask us to do a problem. And here's another picture, which looks useful. Projection of U onto V over here, which is this over here. Let me second. Here it is. Okay, so they ask us to find a projection of this vector U along this vector V. And because that we are using the dot product, meaning in general, finding such a thing using cosine and sine might be a little tricky. But if you have the dot product, then it's actually not that bad. So again, using the formula, we need to know what U dotted V is. What is this dot product? So that's going to be 5 times 4 plus 4 times 1 plus 2 times -3, which is -6. And this is going to be 20 minus 2, which is 18. So that's U dotted with V, 18. And so we have one part of what we need. We need U dotted with V. We need that. We need the magnitude of V. And actually, that's it. We don't need any other piece of information. Then we can put all these pieces of information and get our projection. So what is the magnitude of V? So the magnitude of V is the square root of 16 plus 16 plus 4, which is the square root of 36. So the magnitude is 6. So we have 18 for the dot product and 6 for our magnitude. So then we go here and say that our projection of U projected onto V is equal to 18 divided by 6 times EV, which is going to be 18 times divided by 6 times 6. I'm just going to move for the EV, I'm just going to, it's V over the magnitude of V. So I'm just going to move this magnitude over here times the vector V. So what's our vector V? 4, 4, 2. So this is 18 divided by 36 times 4, 4, 2. Okay. Yep. And this is a new vector. It is going to be 4 divided by 2, 4 divided by 2, and 2 divided by 2. And this is our new vector. So this is the projection of U onto V. Any questions? Yes.
Could you go to your work for a second? I'm still a little confused how you got the second 6 in the denominator, so this is 36.
Yeah, so this EV, this EV is equal to V over the magnitude of V. We know the magnitude of V is 6. So this is really 18.
Oh, I see.
All right.
Yeah.
Any other questions? Yes? Yeah. So this is 18 over 6 times V over the magnitude of V. That's what this thing is over here. The EV is V over the magnitude of V. We know that the magnitude of V is 6. So this is going to be 18 divided by 6 times 6 times V, and that's what you get here. Any other? Yeah.
So what did you get here?
Yeah, so here it is, the answer, it's a vector. So the component of this vector is 18 over 6. 18 over 6 is equal to the component of the projection of U onto V. That's the length of this vector. And then you take that and you multiply it by your unit vector, and you get another vector, and that's your projection right here. This is the projection of U onto V. Any other questions? Okay. Now, once you have your projection, you can find the orthogonal component of your projection. And we denote that by this, U orthogonal to V. So that's this vector right here. Every vector, you can project it onto another vector, and then you can find the other components such that if you add them, you get back your original vector U. So, for example, if I have some vector, let's take the vector 1, 1. So here's your vector 1, 1. And I wanted to project this vector onto the vector I, which is the vector 1, 0. What will this projection look like? Well, let's do it quickly. First, you need, so this is going to be your U, and this is going to be your V. So you're looking for U projected onto V, which is equal. So first, we want to find the dot product. So let's find the dot product over here. U dotted with V is going to be 1. Now we need the magnitude of V. Well, the magnitude of V is also 1. So this is going to be 1 divided by 1 times EV, but EV is already just 1, 0. So that's going to be, I mean, I is already the unit vector in the direction of V. So that's just going to be 1 times I, which is 1, 0. And that's just 1, 0. So that will be your projection, which makes sense. It's kind of like you're just ignoring the Y component. So what's the orthogonal part of this projection? Well, that's kind of like you're projecting this in this direction, or you're finding the component such that if you add these two, you get back 1, 1. So what vector do we have such that if I take U projected onto V plus U with its orthogonal component, do I get 1, 1? I'm trying to recover 1, 1. I'm trying to find the component that is the projection in the direction of V, and then whatever it is that's left that we just got rid of while doing this projection. So always some information that we erase, and that's what we're trying to find. So this is 0, 1 plus U orthogonal to V is equal to 1, 1. So anyone can tell me what is U orthogonal to V? 0, 1. So that's just a very simple example, which makes sense. This vector 1, 1 has a x component. And if I project it into the x direction, I recover that component. I recover the x component, which is this over here, 1, 0. And then if I want to recover the original vector, I just have to add whatever y component there was that I got rid of, and I recovered the y direction. And in this case, it's 0, 1. I basically erased this 1 when I projected, and now I recover it. And that's this formula over here. So if you want to find the orthogonal vector, you just move the projection to the other side. So the orthogonal vector, very simply, is u minus the projection of u onto v. That's how you recover your orthogonal component. Yes. Sorry, what?
What you're writing in front of the screen at the bottom.
Oh, here? Okay, I got it. Okay. Okay, so now they ask us, sorry, give me a second. Okay. So they ask us, to decompose U with respect to V, which means find the projection and find the orthogonal component. Well, so let me write this in another page, 5, 1, -3. So U is equal to 5, 1, -3, and V is equal to 4, 4, 2. 4, 4, and 2. Actually, everyone take a couple of minutes and try to find the decomposition. So try to find the parallel part and then subtract that from U, and that will give you the orthogonal part. And then I'll do it. Okay. So in order to find the projection of U onto V, well, this is going to be U dotted with V over the magnitude of V times V over the magnitude of V. So what's U dotted with V? It's 20 plus 4 minus 6, which is 18, So I guess, yeah, same. This was right the problem that we did. And the magnitude of V is going to be equal to the square root of 36, which is 6. So U projected in the direction of V is going to be 18 over 36 times 4, 4, 2, which is equal to 2, 2, 1. And then its orthogonal component. So U orthogonal to V is U minus 2, 2, 1. So U orthogonal to V is going to be equal to 4, 4, 2 minus 2, 2, 1, which is 2, 2, 1. Oh, I put, sorry, what? 1, 5, 1, negative 3, yeah. 5 times 4. Sorry, what?
The last line. You put in 4, 4, 2.
Oh, got it. Thanks. 5, 5, 1, negative 3. 5, 1, negative 3. Okay, so this is going to be 3, negative 1, and negative 4. Okay, and then we can recover U by just putting those two things together. So U is the projected part plus this thing that we just found, 3, negative 1, negative 4. Any questions? Okay. So I'm going to skip this this physics problem, but again, if you have questions about it, you can definitely come ask me. But basically, it's a problem about finding the parallel or an orthogonal components to some force vectors. And I'm also going to skip this physics problem. So let's try to summarize what we did. We have the dot product is multiplying each component of our two vectors and adding them. We saw some of the rules about the dot product, but like I said, these rules are very intuitive by what the dot product just is. So you shouldn't memorize them. If you need them, you can always recover them. The most important formula that we saw with the dot product is V dotted W is equal to the magnitude of V times the magnitude of W times cosine theta. We said that if two vectors are orthogonal, then their dot product is equal to 0. If they're parallel and they're the same, then they're 1. And then we showed that every vector can be decomposed with respect to a different vector into its projection and its orthogonal component. And we said that the formula for the projection uses some constant multiple, which is U dotted V over the magnitude of V, times the unit vector in the direction of V. So that's how you do projections. And the main thing to remember, I think the main two formulas to remember is this formula and how to recover. You don't have to memorize it, but how to recover the angle from that formula. You can always derive that. Okay, some lines are missing. Anyway, so how to recover the angle formula. So that's 1. And let's say 1.5. And then the second formula to remember is this formula. But specifically, I would recommend remembering U orthogonal to V is U dotted V over the magnitude of U times EV. And then in order to find the orthogonal component, well, that just takes, you take U and you subtract your U and its projection. You take U and you subtract the projection of U onto V, and that's how you find the orthogonal component. So that's the dot product part of this. Any questions before we continue to the cross product? Sorry, what? Sorry, B. Okay. I would recommend trying some of these examples. Definitely compute the dot product a couple of times just to make sure you get a hang of it. It's not that hard. And then try to find the angle between vectors. Again, once you can compute the dot product, and once you know the formula for magnitudes, then this is also fairly straightforward. And then take a couple of projections. And once you can do that, then you have this chapter complete. And if you have any questions, definitely let me know. Okay, so the next topic is the cross product. And there are two operations that we learn to do on vectors. The first one is the dot product, and it corresponds to cosine, like we talked about. And the second one is the cross product, and it corresponds to sine. But of course, it does other things, so we will talk about. And I would also say that the dot product is kind of the way we find angles, and the cross product is the way we find areas. So two very important mathematical things, angles and areas, and we have two corresponding operations to solve for those type of problems. Okay. So before we start with the cross product, it's important to know what a determinant of a matrix is. And here we have a determinant of a 2x2 matrix. So when we write matrices, we write them with normal parentheses, A, B, C, D. And if you take linear algebra, you will see that this corresponds to a linear transformation of a vector, which we don't need to know for this class, but what we do need to know is if this is A, the matrix A, then the determinant of our matrix A, which we write with two lines, A, B, C, D, is equal, and then you take A times D, so A times D minus B times C, B times C. And that gives you some number, and that number is your determinant. And if you do know some linear algebra, you'll know that this corresponds to some area. If I take a little box, so if I take a little box in R2, here's X, here's Y, and imagine that this box has area 1. And then imagine I apply the linear transformation A, B, C, D, and I get a parallelogram. So maybe I get something that looks like this. So that's what happens when I apply the linear transformation of that box. And if you want to know what this area, the area of this parallelogram is, well, that's the determinant of, here's your A, that's the determinant of A. So for example, if your linear transformation was 1, 2, 1, 1, your determinant is going to be 1 times 1 minus, I don't want to do negatives, and I don't want the determinant to be 1. So let's say 1 times 3, and then let's have a 1 here. So this is going to be 3 minus 1, which is 2. That's your determinant. That's the determinant is 1 times 3, 1 times 3, minus 1 times 1. And that tells you that the area of this new region is going to be 2. So you took a box with area 1, and now you get a parallelogram with area 2. And I don't want to go too much into this, but it is very important to know for linear algebra. And what's important for us to know is this operation right over here. The determinant is AD minus BC. And we need to know it for a matrix, a 2 by 2 matrix. And we need to know a similar operation for a 3 by 3 matrix. And that's it for this class. We don't need to know anything else, no higher matrices. But the question is, what is this for a 3 by 3 matrix? So let me go here. If you want to take the determinant of a matrix with coefficients A1, A2, A3, B1, B2, B3, C1, C2, and C3. There are 2 ways that I know to do this. I think the best one is what I'm going to explain right now, which is you go to your first row, which is this row. You take this A1 and you put it here, A1. And then you take the determinant of the matrix that you get from blocking out these 2 lines and looking at this over here. So that's B2, C2, B3, and C3. Okay? Then you erase these lines. You go to your B1. Because you moved 1 column, you put a negative. You take that B1 and you put it here. You again imagine that these lines are erased, and you put the resulting matrix, the A2, C2, A3, and C3 in that matrix. So now you want the determinant of A2, C2, A3, and C3 over here. You then again erase these lines. You move to your C1. Because you moved again, this becomes plus, so it goes back and forth, plus, minus, plus. So now you have plus over here. C1 times the determinant, and then you erase these lines and you put an A2, B2, A3, B3. Any questions so far? And now you use the rule to find the determinants of each one of these 2 by 2 matrices. So the first one will be A1 times B2, C3 minus B3, C2 minus B1 times A2C3 minus C2A3 plus C1 times A2B3 minus A3B2. And this is some number. If all your original coefficients were numbers, then this is some number. And that number is the determinant of that 3 by 3 matrix. Any questions? Okay, if you haven't done these type of operations before, do a bunch. We will be doing them a bunch of times in class, so you will learn how to do them. And they appear on homeworks. It's an important operation to know how to do. Now, you don't only need to do this with numbers. You can put vectors into your matrices. But before we do that, let's go back here and look at this formula. So this is the formula. This is the formula that we just mentioned. You would do the A1 for the first one, and then you erase this and you get B2, C2, B3, C3, and then you continue. And remember to put a negative sign at the next step and then a positive sign at the step after. Okay, so an example. They want us to calculate the determinant of 2, 4, 3. Let me write this somewhere. 2, 4, 3, 0, 1, negative 7, 0, 1, negative 7, negative 1, 5, 3, negative 1, 5, 3. So again, you go to the first part, you write down 2 times the matrix 1, negative 7, 5, 3. Minus second component 4 times the matrix 0, negative 7, negative 1, 3. Plus 3 times the matrix 0, 1, negative 1, 5. Okay, please take 2 minutes and finish this problem. Yeah. Okay, so I'm gonna write it here somewhere, 47. Okay, so let's try to do it. So we're gonna have 2 times 3 minus minus, which is plus 7 times 5, minus 4 times 0, then minus minus, and then another minus, so 7, plus 3 times 0 minus minus, which is positive. let's see. Um, right, okay, minus, and then, right, I agree. Okay, so, sounds good. Okay, so 3, negative, negative, and 2 times 38. Sounds good, okay? Yeah? Any questions? Okay, so let's finish here. Actually, we have 4 more minutes. Sorry, so let's just do this with vectors, and then we're gonna finish after that. So we can find the cross product with constants, or we can find the cross product with vectors. So if you have 2 vectors, you have the vector v, which is equal to v1, v2, and v3, w, which is equal to w1, w2, and w3. You want to find the cross product between them, and we say that that's going to be v cross w. That's going to be the determinant of the matrix I, j, k, and you're going to do this every time, make a matrix like this. And then you're going to put v1, v2, v3, w1, w2, w3. Okay, so the I, j, and k go on the top row, and then you put the v on the second one, the components on the second one, and then you put the w on the third one. And so then when you try to find this, this will be I times the matrix, the determinant of the matrix v2, v3, w2, w3, minus j times the matrix v1, v3, w1, and w3, plus k times the matrix v1, v2, w1, and w2. Any questions? So you're doing the same thing that we did before. You go to the first component, you put that here, you erase the 2 lines, and then you put this matrix, the resulting matrix here, and you take its determinant. Go to the next one, minus j, and you erase these 2 lines, and then you get v1, v3, w1, w3. And then in the last step, you're going to do, so let me write this in component form. In the I1, you get v2, w3, minus v3, w2. In the next component, you get negative v1, v3, minus, sorry, v1, w3. Minus w1, v3. And in the third component, you get v1, v2, minus w1, w2. And we're going to review this again next time we meet. Try to do dot products, projections. You don't have to worry too much about the cross product yet, so focus on the dot product, okay?